Bansal, and we'll be speaking on reliable object detection and identification in adverse conditions. Mr. Bansal is a computer science PhD candidate at the University of California, San Diego. He is a part of wireless communication sensing and networking group headed by Professor Dinesh Baradia. His primary research interest lies in the fields of automotive imaging radar, computer vision and signal processing algorithms with applications both in indoor and outdoor domains like perception and adverse weather conditions, infrastructure sensing, and so on. He has worked on building real-time, safety-critical, and reliable perception systems that use multimodal sensing from cameras, radars, and lidars. His work has been published on top conferences such as Census and featured in several press releases, including Wall Street Journal. Before we move on to the talk, we would like to request the online audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. Finally, we request the online audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you may unmute yourself and ask Mr. Bansal directly. Over to you.
Thank you. I hope everyone can hear me right. Okay, so hi everyone, I'm Kshitiz. First of all, a big thanks to Professor Rajesh and all the CNI organizers for giving me an opportunity to talk here at ISC. I remember when I was young, I always wanted to come to ISC, and today I'm standing here giving a talk. So quite excited to be here. I am a fifth-year PhD candidate, and I work with Professor Dinesh Baradia. And today I'll be talking about my research thesis, which is on reliable sensing and adverse conditions. Hopefully, you will enjoy the talk and feel free to ask me any questions you have during the talk. So, autonomous driving is one of the most sought-after technologies in today's time, right? And the impact is visible almost everywhere, right? From self-driving to areas like long-haul trucks, agriculture, mining, and many more, making all of these much more efficient and much more safer as well. So let's dive a little more deeper into understanding this driving. SAE International is a board that defines 6 levels of automation, which is taken as an industry standard by all the automakers. Among these 6 levels, level 1 and level 2 are what are called as driving assistant features, and this include things like cruise control or lane assist. Level 3 onwards is what we call as self-driving, where level 3 still requires human supervision. Level 4 can go full autonomous, but only a few limited areas. And level 5 is where true autonomy takes place. To give you some more context, our well-known Tesla lies somewhere between level 2 and level 3. And more recently commissioned Cruise or Waymo in San Francisco, they lie at level 4 because they can operate without any driver in certain limited areas of San Francisco. Now the question is, what are the challenges that are required to be overcome to operate at level 5? At this level, we have to operate without any supervision at all, and this includes all the areas, also including adverse conditions, for example, fog, dust, and rain. Right? And let me show you some examples of what these challenging conditions are. So here is an example where a person is driving their car, and as you can see, there is a lot of fog going on. Due to this fog, we cannot even see, I guess, more than 10-20 meters in front of you. That on a highway. Naturally, this is an extremely dangerous situation, and you can see, had this car not put on their brakes, this could have been proven to be really fatal. And this is a very common occurrence that happens every year on Yamuna Expressway. You might have heard of it. Similarly, there is another example here. Right? Look at the red car, which is trying to change its lane, right? And suddenly a truck appears from the next. Fortunately, the car was able to make the turn at the right moment, but let's say it was not able to see that truck coming from the front, it would have been proven to be really, really fatal. So these challenges overall put a lot of pressure on the perception system, because perception system is something that is really required to provide the information about the environment around, right? And it does its job by relying on a lot of different sensors. So let's look into what these sensors are. The most commonly used sensor is camera, which relies on ambient light, right? Everyone knows what a camera is. The second one is lidars, which use these laser signals, which actively transmit this laser in nanometer wavelength, and it measures the depth of different objects in front of it. And more recently, people are looking into millimeter wave radars, which similar to lidar, they produce active signal, but in a different spectrum of millimeter waves, which is somewhere around gigahertz frequency. And these sensors provide the high quality data, which has been able to achieve up to level 4 of self-driving, as we saw with the cruise or Waymo of today. But the real question is, how do these sensors really perform in adverse conditions, right? Because that is what is required for level 5. So here is a study of when we subject a lidar sensor to different fog densities, right? As the fog level increases from top to down, we can see the perception range of the lidar really decreases by a lot. And the reason is that the lidar operates at nanometer wavelength, where the size, wavelength of these signals is similar to the size of fog or dust particles, and hence it cannot easily pass through. Similarly, for cameras, again in the visual spectrum of nanometer, having, as we also saw in the previous example, it faces a lot of difficulties in seeing through these adverse conditions. Due to this particular reason, recently researchers have been adopting automotive radars to tackle these challenges. Automotive radars, the very cool thing about them is, as I said, they operate in millimeter wave regime, where the wavelength is big enough to pass through these fog or dust particles, right? And this allows them to be a truly all-weather sensor. So the problems of not being able to see through the dust is not there. On top of that, radars can also provide very good features. For example, it can penetrate through occlusion. So if there's a pedestrian standing in front of a car, then these millimeter wave signals can bounce through the ground and make the perception of that hidden obstacle, hidden object possible as well, which is not there, which was not possible in case of. I think I would get the right.
We can continue. But is it in the Zoom? Is it coming through?
I think nobody has said anything. No one has said anything, sir.
You can continue. You can continue.
Okay, awesome. So that I'm now. Okay, so yeah, so like I said, these automotive radars can actually penetrate occlusion by bouncing these signals off of the ground. And another good feature is that since these radars can provide you really long range, right? So larger the wavelength, farther your signals can travel, and hence you will get much more range compared to your lidars and cameras. A tweet from Elon Musk really captures this perfectly, right? When he was asked that why don't you use lidars in your Teslas, he said that if you were to use any active photon generation, any active sensing, then might as well use an occlusion penetrating wavelength, like for example, precision radar at 4 millimeters, is a millimeter. You might not agree with Elon Musk on a lot of different things, but this is something that I can agree with. So this finally brings me to the research thesis, my research thesis, which goes as safe and reliable autonomy and adverse conditions can be enabled using active sensors at millimeter wave frequencies, which are millimeter wave radars, and develop a system that provides high quality data to improve the strength of the perception systems, semantic understanding so that you can understand the scene in more detailed manner, and contextual information that is eventually going to help in driving. And this is exactly what I'm going to talk about. I'll talk about 3 different projects. The first one will talk about how we improve the perception performance from radars. The second project is RAT-SegNet, which talks about how we use radar and cameras to get more semantic understanding or more detailed understanding of the scene. And the third one is our fiducial, which talks about how we can augment the infrastructure elements to get more context out of the environment. And I'll go into more detail about what all of these terms mean, right? So just take it. Okay, so let me start with the first work, quantilism, that provides accurate perception in adverse conditions. This work has been published in Census 2020 conference. So before I go into that, into quantilism, let's first understand what do I really mean by perception. A lot of you might be thinking I've been talking about perception, but what really it means. So a control system of any autonomous agent, right? This requires information about the environment, right, to perform things like path planning or navigation. This information should come into the format of precise locations and the dimensions of all the objects present, right? So, for example, if there are two cars, we should know that there are two cars and they are present at these locations. And the role of the perception system, hence, is to predict these bounding boxes for each of the objects of interest. So, as you can see in the graphic, the goal is, given the sensor data, tell me where all these objects are in form of these bounding boxes, right? So we need accurate bounding boxes from our perception system. That is the objective of perception. Now, if you really think about it, right? I've been talking about radar, but you might ask me that these radars have been there since ages, right? Then why don't we really see them ubiquitously being deployed in autonomous cars? So, if you think about it closely, traditionally the radars have been used to detect aerial objects, right? For example, airplanes and all, where even detecting these objects as a point is enough. But now the game has changed a lot, right? Detecting these vehicles just as a point object is not going to be it. What you really need is to get a lot of points around these objects so that finally you can put these precise bounding boxes around these objects, right? So, the point is not enough, or what you need is these big high density of points around different objects. So only once you achieve that, you are going to do complex tasks like path planning, right? You just cannot plan your path around these points. Then you are definitely going to crash into one of these objects. This brings me to pointillism. Let me tell you where this word pointillism comes from. It's actually an art technique where an artist uses nothing but points to create this artwork, right? Individually, each of these points do not mean anything, but a very good, perfect combination of them creates such an amazing art. Similarly, in the world of automotive radars, we create a high quality radar point cloud through our work pointillism. And we also propose a deep learning based solution that takes this high quality point cloud and converts it into the bounding boxes that we need. We also provide during this work the first open source large scale label data set. I was talking to Peter about it today. This data set business is a very big problem for radars, right? And we were one of the first ones to create a data set which has these data from different synchronized sensors, which included radar. And finally, with all this, we get the accurate and the all-weather reliable perception that we really started off to seek. So let's also look into what is the difference between the different point clouds coming from these different sensors, right? So specifically, what is the difference between the radar and the lidar? So for example, let's say there's a scene where there's a car, right, and you are trying to sense it with different kinds of sensors. This is what a point cloud would look like as seen from a lidar. You can very clearly see that the number of points is a lot, and you can see the shape of the car. Very easy to see that, very easy to tell that, okay, there is a car standing here, right, or there. For the same scene, the point cloud of the radar looks like this. Now, from the very first look, you can see the enormous difference between the lidar point cloud and the radar. The density of points is so less, and the shape of the object is also not very clear. And the reason behind this is actually a very fundamental physics. Right? The lidars, which operate, as I said, in nanometer wavelength, at this wavelength, all the surfaces that we encounter, their micro roughness is so that the signal falling onto them, this nanometer signal falling onto them, scatters in all the directions. This is exactly why we are able to see all these objects around us, right? The same thing that goes on behind the visible light. And when that happens, the signal will also travel back into the direction of incidence, right? And you can be sure that whatever signal you send, you're always going to get something back. And hence you see a lot of. But for the radar, which are working at millimeter waves, most of these surfaces act as specular or mirror-like surfaces, and most of the energy just gets reflected away from the radar. Right? So this might cause you things like blindness, and a lot of times you will not get any reflection back to you. So we saw that specularity becomes a very big challenge when we are dealing with these radars, right? One solution that people think of doing is that why not replace this a small radar with a high resolution radar, which is the industry standard these days, right? This high resolution radar has a lot more antennas on it, providing you a better resolution. Even that will have the same problem, because this is a problem of physics which you cannot solve just by having more resolution. Just by sending more rays, it's not going to solve the problem. So what do? This is where, to overcome this adverse effect of specularity, what we propose is that rather than putting a lot of antennas at one location to make it more high resolution, use a combination of multiple radars that are placed at some strategic vantage point, and this effectively creates a large virtual aperture. And this combination now quite effectively diminishes the effect of geometry and the problem caused by specularity. So while traditionally multiple radars or multiple sensors in general are used to create a wider field of view, what we propose is that you create a high quality imaging region by facing both the sensors in the same direction. And in this common field of view, you are going to get a much higher quality point. And to see the proposed system in effect, right, consider a scene with these three cars as shown here, right? When I collect the data from these three cars only by using a single radar, sorry. When I collect the data for these three cars, by just using a single radar, you can clearly see that I am getting data from the car in the back and the car in the front, but I am completely missing the car in the center. But when I collect the data with multiple radars, again placed at some strategic vantage point, right, then we start to see even points that I was missing before, right? So this clearly shows that multiple radars placed at an optimal separation captures many more features of the environment and diminishes the harmful impact of specularity. More details about how we get this optimal separation is in the paper, and I can talk offline if anyone is interested how we find that. Okay, so the question is that enough? Is the problem solved by just using multiple radars? It turns out it's not. There is one big challenge which is still there, and that is radar's noise. A radar contains noise because a lot of background clutter, multipath, and all these things. And the problem with naively just adding two radar point cloud is that you are adding their noise as well. So think of adding two noisy signals. You are going to add their noise as well, making your signal more noisier than before. So for example, let's say there is an automotive scenario here, right, where there is a source vehicle trying to sense a target vehicle by using two radars. And the radar point clouds are shown here by the red points and the green points. So you can see that along with the target points, the noise points are also getting added, right? And this is really going to have a harmful effect, because now you will start creating false boxes around these points, and your control system would be like, okay, there is an object here, so I cannot go here, right? So clearly messing your downstream tasks of navigation and broadcast, which is definitely something that we don't want. Our system pointillism actually proposes another novel way of combining these data from multiple radars that actually removes the noise as well from the single from these point clouds, right? So, and I'll tell you how. So consider a setting here, right, where there is a metal railing and a car is again trying to sense a target vehicle with one radar, right? It gets a point from the target vehicle, but at the same time, due to the reflection from the metal railing, it also gets a ghost object onto the other side. Now, by just having this single radar data, there is no chance, or it's very hard to differentiate whether this is a true point or a ghost point. Now, consider another radar, right, on the same car doing exactly the same thing. We having a reflection from the actual target vehicle and also creating a ghost object. Now you can clearly see the difference. Right? The separation between the target points is much less compared to the separation between the multipath noise points. And there is something that we really bank on, and we define a potential or confidence of sorts, which is inversely proportional to the separation of points between the point clouds from two radars, right? And we use this to identify what point belongs to noise and what point belongs to the target vehicle. Then you can also think of it as spatial averaging to reduce the or to increase the SNR of the signals that you are getting from two different sources, right? We call this combination as cross potential point clouds because we are creating a potential between two different point clouds. Now, the very important thing about this cross potential point cloud is that what kind of threshold you set to remove the noise, right? That is going to really matter a lot. Again, consider a scene where a car is trying to detect two vehicles, right? Shown here as the bounding boxes, the green bounding boxes, and the blue and the orange line is showing the heading direction. Again, the red and blue points show the point clouds from the two different radars. When I put a threshold of 0.5, I successfully clear out the red points which were the noise from the first radar. Right? But if I try a more violent threshold, I might end up losing more useful points which were actually inside the bounding box. Right? Going further down the lane, 0.9 might actually cause some of the objects to completely disappear. Right? So it's very important of which threshold you choose for this cross potential point. Okay, so till now we have successfully defeated the specularity by using multiple radar point clouds. We have also tackled noise by creating the cross potential point cloud. But our ultimate goal was to create these 3D bounding boxes around the object. Right? So for that we proposed a 3D a deep learning technique, right, called RPNet, which takes these cross potential point clouds and converts them into the bounding boxes as required by the downstream task. And this is the overall architecture of RPNet. I won't go into too much of details about this, but overall it contains two stages of first finding out where the objects are, and the second stage of defining the sizes of the bounding boxes at those locations where it has found the object. I call it the region proposal stage and the refinement stage. Again, we can talk offline if anyone is interested, but due to the time constraint, I won't go into detail.
One question.
Yeah.
So are you using only lidars and radar for this?
So this one is only radar. Only radar. We are contrasting with lidars because to show what are the challenges when you're dealing with the radar. But since the objective is to make perception possible in adverse conditions, we are only allowed to use radars because lidars won't work in those conditions.
So why not use combine the input from say visual spectrum information technique and with the bounding box?
Yeah, so that's the next topic that I'm going to talk about, which is how do we fuse the camera with the radar. I think I got disconnected from.
Yeah.
Okay.
Yes.
You're back.
Yes.
Cool. So, yeah, let's go. Okay, to implement this pointillism, we combine the data, we combine lidar, camera, and data into a single system and put it on a car and collect data around the campus. Again, here I'm using lidar and camera only to get ground truth boxes so that I can train my deep learning network in a supervised manner. But the final system only makes use of the radar data to get the point. The data set that we collected contains around 54,000 radar frames, 3D bounding box labels from all these things like sensors, 5 real-life traffic scenes, and multiple operating conditions that include fog as well. And let's talk about a few results that we achieved by this work of ours. Right? I'm going to use MAP metrics, which stands for mean average precision, which is a standard metric used in object detection. It is a combination of precision and recall, meaning to say that you are making your higher recall means that you are getting all the objects, and higher precision means you are making less mistakes, less false positives. Right? So if both precision and recall are high, your average precision would be high. Just a crude definition of this term. So let's start with point RCN. Point RCN is a technique which has been developed for getting these 3D bounding boxes on lidar data. We used it, retrained it on our radar data, and we got this performance. As you can see, the performance is quite bad, which says that directly using a lidar-based network on the radar data is not good. Then we developed another technique based on clustering. Right, this is a non-deep learning technique, and hence it does not have any special refinement of the bounding boxes. Right. We use this technique to show the importance of using deep learning, and as you can see here, the performance also is as bad as point RCN. Going one step further, we added our cross potential point cloud formulation in this clustering technique. We saw a little bit improvement in the performance. Now now this is the performance of our entire system pointillism, which is the multiple radars and cross potential point clouds trained by using RP9. And you can clearly see the huge jump or huge performance difference that we get with RP. To do some more ablation studies, we remove the cross potential point cloud without doing that thresholding. We just use the naive combination of point clouds, and we saw some decrease in the performance, showing that how cross potential point clouds noise removal is actually making a difference. And further, this is the performance when I just use single radar. I don't use multiple radar, just train my entire network on the single radar data. Again, there's a drop in performance showing that by using multiple radars, we are actually able to get a lot more features of the environment as well. So this clearly shows that RPNet outperforms all the other baselines, right? And the effect. This also shows the effectiveness of our approach, both in terms of noise removal and bounding box prediction from radar point. So here are some demonstrations of our system. Right on the left, this is the bounding box predicted by just using the radar data, and we throw a lot of fog onto the scene, and you can see in a few frames the car is completely occluded because of fog. But this bounding box is still very clearly being predicted, right, by using the radar data, which is showing that we are able to achieve as the reliable object detection as we expected, even in the adverse conditions. And on the right, I compare the radar and lidar depth estimate of the same scene, and you can see the radar is consistently providing the correct depth as the blue curve, and lidar keeps on making a lot of mistakes because of this fog obstructing its view, right? Which shows that radar can really work well in these adverse weather conditions. Okay, so let me pause here for a minute if there are any questions.
Is there any correlation with the previous time frames for the next present prediction?
So you can definitely do that. In this particular work, we did not do that. There was though a Kalman filter based pose estimation correction, right, which was not deep learning as such, but there are approaches where, and actually this is very common to be done in radar because radar data is very sparse, right? Very less point. So people combine data across multiple time frames to make it more denser, and then do perception on that. So that is definitely something you can do, and that module can be added on top of what we have done. So yeah. Okay, so till now we saw how radar modeling box performance can be improved by using multiple data, right? Our goal of level 5 self-driving demands a really good and reliable understanding of the scene. Radars provide us precise depth, they provide us occlusion penetration and bad weather sensing. But the one thing that they miss out on is the texture or the color. And we as humans, we really understand the importance of colors, right? Because that's how we see the world. So naturally, using a camera can add this missing information into your sensing stack, right? By providing you high resolution texture and scene understanding. So this brings me to my second project of radar and camera fusion. When fusing camera with radar is a hard problem, but reliably fusing camera and radar is even harder problem, right? And personally, all the companies that I've talked to, they are still trying to figure out what is the most optimal way of fusing radar with camera. There is not a solution that everyone has accepted till now. We know that radars and camera, these two sensors provide complementary information, right? Why? Because camera provides you a lot of texture information, which radar does not, and radar provides you very good depth information or very good bad weather performance, right? So what a perfect fusion should look like, it should be complete, that it should make the best use of both the modalities, modality being the camera and the radar, and it should be reliable. It should ensure that the adversities of one sensing solution should not affect the other sensor, right? Because if one sensor being bad is taking down the performance of the entire system, then I'm doing no good. So let me actually first tell you how the past work that has been done in this radar camera fusion has fell short of achieving these two important requirements of a perfect fusion, right? So the first class of camera radar fusion, these views and try to fuse it at a feature level, not going into too much detail, right? But then this is how they were able to make use of both the front and the top. But the problem with this approach is that they are extracting features from both the views, and then even though I'm using radar and camera as two separate streams, when one of them goes bad, the entire system, the entire performance goes bad. So this definitely makes it unreliable in adverse conditions, and hence not the most optimal way of doing the fusion. In our work, Rats and Net, we propose a totally different philosophy of radar camera fusion. And this philosophy is based on the independent feature extraction of camera and radar. As I said, we note that both the modalities are contributing different information, right? So we say that why not extract that information independently and then fuse it later. Cameras are providing rich semantic information, so you extract that from the camera. And radars are providing the adverse weather perception and occlusion penetration, so use that separately from the camera. So let's first talk about what we do with the camera. Right? For the cameras, as I said, they provide rich semantic information. So we use this technique of image semantic segmentation. Some of you might have heard of it, right? What it does is that for this entire RGB image, it classifies each pixel into what class it belongs to, right? So for example, here, it is classifying all the pixels into whether it belongs to a car or not. So the result, as you can see there, all the purple pixels as identified by this image semantic segmentation belongs to the car, right? And everything else at the background is yellow, right? So now you have this information of where all the cars are. And you can do the same thing for all the different classes, which includes pedestrians, traffic signs, trucks, trolleys, whatnot, right? And this is how we are extracting the semantic information from the camera. Now let's talk about how do we combine this semantic information, how do we propagate this semantic information into the radar point cloud, right? And we do this by using a technique called SPG encoding. So this is an example image, RGB image, right? And this is the bird eye view point cloud from the radar. It looks a lot noisy, right? But trust me, there is a lot of order if you look at it from my eye, because I've been seeing it at it for 5 years now. But what we do is we find out association between the objects in this point cloud and the camera image, right? By doing a projection of the radar onto the camera, right? And then for all the points that get associated by a class object, for example, car in this case, we only keep those and remove everything else, right? So to say this in the simple word, right? First, I perform semantic segmentation of the RGB image. I get all the pixels which belongs to the car. Then I take this radar point cloud, I project that radar point cloud onto that segmented image, and then all the points that correspond to the purple pixels as we saw before, I only consider them and create this semantic channel of car, right? So now you can see that the number of points are reduced, and all the points that belongs to the car are the ones that are present here. Although there are still some problems here, right? There is some noise because I say I am doing this projection of association of radar with the camera, but no association is perfect. There can be misprojections, misalignment and all, because of which I can get some false points, right? And then we also provide a technique called instance informed weighing, right? Again, not going into too much detail, but using this technique, we are able to clear out those noise at the back caused by the misprojections, etc. And finally, we get only the points which belongs to the actual cars, right? So if you see, for example, the front car is this, the three cars at the back are these 3 points, right? So this is how we only get the points belonging to a particular class. And we can do this for all the different classes. Right now I'm showing it for the car. We can do it for pedestrians, we can do it for trucks, right? And imagine it as creating a different channel for each class. This brings me to the SPG encoding, right? The first element of it is the bird eye view, the entire radar map. The second element is the camera semantic map that we just now created. And then there are some point features as well, which are like, for example, the mean and number of points in each grid point, etc. Right? We combine all of that into one big cube of data and then put it into a deep learning object detection network, right? And which provides us with the object boxes or the 3D model boxes as required, right? And the effect of it, now if we see the same example, AVOD fusion, which was making a lot of mistakes in the foggy weather, our approach RAD segment, it keeps performing similarly in both good and bad weather because we have removed this strong feature dependence on between the camera and the radar features, and we are not, and when the camera performance goes bad, we are not getting affected as. So these are some numerical results, right? Compared to the AVOD fusion, which is the state-of-the-art radar camera fusion network, we are doing plus 27% better MAP points, right? We also compare, for example, when we don't use camera at all, then we get performance around 36, which shows why using camera or how much difference does it make to use camera. And just for completeness, we also use just the lidar in camera with the same network that we had at Satellite, and we still saw the radar perform better because, like I said initially, that radars can get longer range and can penetrate through occlusions. This is on, so this result was on the Asterix data set. We did similar on another data set, which is called Radiate, which is a different type of radar, which is a mechanically rotating radar. Just to show that our approach is generalizable across different radars, and we saw a lot of performance improvement compared to AVOD fusion in all clear adverbs and clear plus adverbs. Okay, so any questions?
What was the time taken for doing this inference or objective detection?
So for this particular, we keep it real time, right? So real time meaning anything below 20 milliseconds is good enough, right? And it depends on different networks. Like the most time taken of part would be the inference of the neural network at the end, right? And since the approach that I am using, it's a single stage network, right? So it is somewhere below 20 milliseconds. There are some approaches that also break it into multiple stages that can go up to 100 milliseconds or so. But generally, the definition that industry takes for real time is 20 milliseconds. We try to keep it under.
And this could fit into a single
Yeah, definitely. So you can have these like NVIDIA Jetsons and all that can run these neural networks. And these days, actually, if you do some more engineering, you can convert all this into this floating point into fixed point implementation. You might do that on some performance, right? But then you can make it really, really fast. Again, depends on what kind of application you're looking into, right? So if let's say you are doing self-driving car on a very busy urban scenario, then you cannot do that on any performance, right? But let's say you are doing, for example, self-driving tractor on a big open farm where the number of objects are very less and they occur very infrequently, then maybe you can get away with giving out on some performance and getting more fast results. Cool. Okay, so yeah, let's get back to our original vision of achieving the level 5 autonomy, right? And see what more is required. We saw how pointillism gives us high resolution, high quality data. How RAD segment was able to improve the semantic understanding of our system, right? But in addition to all this, we the one more important thing that is required for level 5 is the scene context, right? And this is something that we all use while driving. And this is where I talk about my third project called our solution. So let's first see what is this context that I'm talking about, right? To give you some examples, we need to understand the intent of the vehicle, right? So for example, when we are following a vehicle, we need to know whether it is turning left or right. Usually, the vehicle is expected to give you an indicator. That's how we know whether it's turning left or right. There are things like traffic lights. You need to know whether the light is green or red. Again, some context required while driving. And then there are a lot of traffic signs that you need to know, speed limits or school zone, all these things. You need to know, again, giving more context about your driving discipline. And more importantly, all this has to happen both in good and bad weather if we were to achieve level 5 autonomy, right? So to bring this context in autonomous driving, we need to sense these different infrastructure elements, right? And hence we develop these R fiducial tags, right, which are millimeter wave backscatter tags, right, which can be used to reliably identify these infrastructure elements just by using a commercial data. Right? This is a project in collaboration with another PhD student, myriad, right? And I'll keep the description of this project short in the interest of time. I'll just go over the challenges and the solutions that we propose, right? But you can think of these tags as long distance RFIDs that can be read by using millimeter wave radar. So there are three main challenges that one has to solve. One is these infrastructure elements are very small, right? So you might not see them a lot of times by radar. They can be overpowered by larger objects passing beside them. Right? For example, if a big truck or a car goes past this traffic sign, then you might not get a lot of signal from the small traffic sign compared to that of a car. Right? And then you also need to differentiate between the signal coming from one type of an object, one type of traffic sign to the other type of traffic sign. For a radar, both of them are just metals, right? Radar is not going to see the color. So we also need to put something that can differentiate between these. But the first challenge, what we do is design these specialized antenna arrays called van array scheme, right? Where these very good quality of these antenna arrays is that it retro reflects the signal, which means that if I'm looking at it from 60 degrees, then it will reflect most of the signal back into the same direction of the signal, which makes the signature of these tags very huge in radar spectrum. So we solve the problem of these objects being small. For this problem of being overpowered by large objects, we create modulation on top of these reflected signals by putting switches right in the tag. So these three black elements are millimeter wave switches. What it can do is it can create on-off switching, and because of that, it can create a specific modulation. So when you see an object in your radar spectrum which is, let's say, blinking, then you know that okay, this is something coming from a tag. Right? And to create an indifferentiable signature on top of that modulation, we also use CDMA codes that can provide a very specific identity, allowing you to operate, let's say, tens of tags at the same time in the environment. And then we perform different case studies, both outdoors and indoors. For example, here we are trying to detect a stop sign placed at 30 meters from the radar in foggy environment. And then indoor, we are trying to find out a fire extinguisher, for example, in case of a fire, when the corridors are very smoky, right, and your cameras cannot see anything. So you paste this tag onto the fire extinguisher and your radar can read it. There's a small demo video as well of fire equipment search in heavy smoke. So what we do is we paste this tag onto a fire extinguisher, right? And then we have a turtle bot that has a radar on it. We have a camera stream of the onboard camera and a range Doppler map of the radar. And on the bottom right is the map of this entire corridor. So the blue point is the current location of this turtle bot, and the green region is where the fire extinguisher is. Right now, when the tag is switched off, we are looking for it, and then we switch on the tag. Once the tag is switched on, then the radar finds the tag, and then you see there are some aberrations going on in the range of the radar. And then we are also able to get a precise location shown by the red dot of that fire extinguisher. And you can see that in this camera image, the fire extinguisher is not visible at all. So you can use these tags in these specific applications where the visibility is bad due to dark or smoke, right? And then can be very helpful for, let's say, fire brigade and all this. And we've been fortunate that our research has been covered by prestigious Wall Street Journal and several other articles as well. And finally, so we talked about three different things of high quality data, reliable scene understanding, more finer context of by using smart infrastructure elements. But all this finally boils down to achieving one thing, which is the reliable deployment of these systems. Right? We have developed all these systems individually, but now comes the question of reliably deploying all of these into autonomous systems. And what it entails is that we need to do a lot of evaluation, right? And for a lot of evaluation, more data is the key. So either we can go out and collect a lot of data in all these conditions, or we figure out a different way, which is to create high fidelity simulations, right, of this radar data. And that's what this is the work that is currently going on, that I'm currently working. We are trying to create these high fidelity radar simulation by using either like a CAD model or even a lidar point cloud. We put it into our simulator and then we can get this radar data. And finally, we can deploy end-to-end solutions on this simulation environment to really test whether all the systems that we have developed really work or not. So this, for example, comparison between the real data and the simulated data, right? So you can see it's again a top view, and then there is a car going around, right? And this, so all the signature here is from the real data, and the one on the right is the simulated data. So you can see we are able to accurately, up to a certain level, match the real data as. And then possibilities are infinite, right? Once you have simulation, right, you can do things like, for example, rather than, so radar has a lot of different configurations that it can have, right? So rather than testing out different configurations, you can first find out what good configuration will work for a particular application in simulation and then only deploy that. For example, here we are doing indoor mapping of a corridor, right? So this is the ground truth. And then on the two figures on the right, the middle figure shows the performance of the real data of configuration 2 and configuration 3. Definitely configuration 2 is better than 3. And similarly, we do the same thing in our simulated environment, which also predicts the same thing, that the configuration 2 is going to be better than configuration 3. So this saves me a lot of time. I can test out thousands of configuration in my simulation rather than putting all of them into the real world, and which is really going to help in deployment of these data. Just a small note on a lot of ongoing work, right? We are also looking into making radar resolution better by using some deep learning classifiers. We are working in explainable AI, trying to get some safety guarantees on a lot of systems that we develop. And then we are also trying to make our simulator more refined by learning radar textures by collecting a lot of data. And yeah, that's all. Thank you all for listening. I'll be happy to take any questions that you have.
I've read about the Tesla cars also, they also use radar and camera images. So, what is the difference in the technology and the field?
Yeah, so actually Tesla has a funny story. They had these back in 2018, I think. They are the ones which are very against using lidar. All the other self-driving companies, they use lidar. So they initially had cameras in their vehicles and then they also had radar. But at that time, I'm talking about somewhere 2018 or 19. At that point, radars were not as high resolution as they are today. So the technology was not as advanced. So they did not see a lot of improvement by adding. When you are adding two different types of sensors, right, that increases the engineering cost by a lot. Right? Let's say if you only have cameras, then you don't need different, for example, data streams going around in your car, right? It's easy to manage stuff. But if you add even a small sensor like radar, then you need to think about things like interfacing and more. And you are only going to do that if the other modality is going to make a lot of difference. At that point in time, they did not realize that they thought that radars are not going to give them much benefit, so they removed it from their cars. Right? So all the Teslas that came, I guess, in 2022 or 2021, they don't have radars. Very recently, there was a news leak that they are bringing the radar back in their Tesla, right? Because now they are more high resolution and everything. And mostly, I think Tesla is still a company which is camera focused, right? So most of their primary perception will still happen with just the camera. For radars, they will use it. So any solution you see in self-driving, right? What is both a lot valuable is redundancy, right? How much redundancy you can get from different sensing modalities, right? So let's say you are getting some output from the camera. You also want to get the similar output from the radar, and then you want to cross match it at the output to see whether the both outputs are matching. This just makes the system more safe. So everyone has their own implementation, right? I personally don't exactly know what Tesla is doing internally, right? But yeah, my guess would be that they would be using radar as an assisting sensor to the camera. While most of my research is primarily focused on radar at the forefront. And even if I use camera, I use it to assist the radar. So if they want to use my research, they can just replace their radar processing pipeline with what we develop here, right? And then they'll still work with their entire camera radar, whatever.
When you are talking about the bird's eye view for radar data, how do you get that?
How do I get that? So radar actually creates a point cloud, right? So when I say point cloud, it means I'm getting XYZ points in 3D. So let's say I put a radar here and I try to sense this point. Then it will tell me that, okay, there is a point at 1 meter X direction at 0,0y. So when I have that data in 3D format, then I can look at it from different views, right? Because it's the 3D data that I have. Right, so that data can be either converted to bird's eye view or front view. It's just about where you are looking at. Imagine, for example, you get these CAD models, right, and then you convert those sketches into front view, top view, because 3D view is the most general view that you have, and then you can project it onto a top-down plane, or you can project it on front plane as you.
So does it depend on multi-path reflections and does it require some objects in the vertical that axis?
No, so that's not a requirement as such, right? So even if you have a 2D radar data, right, you can simply just, for example, let's say you have 10 objects, right? It when we're talking about self-driving cars, right, most of these objects will be on the ground, right? So they won't have much variation in the Z direction, right? Most of them will be at, let's say, a fixed Z coordinate, right? What will vary is X and Y coordinate, XY plane being the horizontal plane, right? So it's just a matter of looking at from the top, right? For example, all the 3D points you get, you remove the slice of the Z coordinate and just plot the XY coordinate in the plane, and that's your top. So because that point cloud is the XYZ point for all the points that are important, for all the objects that are important, just remove the Z coordinate and then you just plot the XY coordinate in a scatter plot, and that is your point.
But what if there is an object which is hidden behind another object?
Yeah, so in radars, there is this good quality that, let's say, even if an object is hidden behind the other object, if the rays can pass, like travel underneath the object and reflect from the object at the back, come back to you. It can even diffract from the edges of the object and then come back to you, right? So all these things happen in radar, and that is why you are able to see points not just from the object in front, but also from the object in front. And that's why I mentioned that using perspective view is bad, because when you're looking at it from the front view, that even if you are getting a point from the object at the back, how do you tell whether it is coming from the back or it's coming from the object at the back? Because it's going to overlap in the front. But if you look at it from the top, then there will be a very clear separation.
As vehicles are moving and we are constantly detecting the signals, doesn't Doppler have it come on?
It does. So radars actually, there is actually a advantage of using radars, right? The way radar frames are, radar is the only sensor right now which can also provide you, I should not say the only sensor, right? But it's the sensor which can also provide you the real-time Doppler of the object, right? So remember I showed you that range Doppler plot. So one axis was all the range and another axis was the Doppler. So each object that is sensed by the radar will find its place somewhere in this range Doppler map, corresponding to, for example, it's at 10 meters and plus 5 meters per second. So it will be at that location. So you are getting both these information at the same time. You might be thinking that the objects move, right? So it might mess up the frame, right? But the frame rates are, let's say, one frame that a radar sends is microsecond in time duration, right? In that time duration, the object moves very, very small distance, right? Which is not even perceivable by you. But you can still use that small movement to estimate the speed of it on, right? So while in the same frame, from one frame to the other, the object might move, but within the same frame, the object will not move as much. But whatever small distance it moves, you can capture it, or you can convert that into the speed of the object. So yeah, that's how the radars actually also always come with the Doppler information of each of these points.
The sensors we look at tags, they are active.
Yes. So they are, we call it semi-active, right? Because they do have active elements in form of switch, right? So you need to put a battery, but then they are so low power that you can operate like one tag with a point cell for, let's say, 10. So again, if you want to increase the range of detection, that you might need to put more amplifiers that will get like eat up more energy, right? But the ones that we developed didn't have any amplifiers, and we were able to get a range of 40 meters.
So just hypothetical situation, what if, let's say, there are some reflective surfaces on the side? Does it impact what you are trying to do?
Yes, right. So, for example, in one of the cases, there was a metal railing on the side, right? It was creating the ghost objects. If that happens, then definitely you will get some like objects that are not real objects, some ghost objects on the other side. And if you use the technique that we propose, the cross potential point, by using multiple lidars, you can actually figure out which point is coming from the multipath because of this reflective surface, and which point is actually coming from the real path.
Thank you, Mr. Bansal, for an informative talk. The link to the slides will be posted on the webpage. Thank you and have a great day. The coffee will be there.
I'll share my email with any of you, and if you have any questions, feel free to contact. I'm happy to chat.